All right, so in 8.4, we're going to talk about z-test for a proportion. So in 8.1 and 2 and 3, we talked about, or 8, actually, really 2 and 3, we talked about the t-test with the population standard deviation known. We talked about t-test when population standard deviation is unknown. And now we're going back to z-test for a proportion. This is not really talking so much about the means and stuff, but proportionally speaking, um, I don't know if you're flipping a coin or doing dice or something like that, kind of what we did back in chapter 2. All right, so objective 7, test proportions using the z-test. So hypothesis test, I don't know why I said it like that. Hypothesis tests involve proportions. Where am I at? Where'd he go? Going the wrong direction. Involving proportions can be considered as a binomial experiment when they are only how many outcomes? Two outcomes. Either the probability of success or the probability of failure, depending on what you're trying to look for. And the probability of success does not change from trial to trial. The odds stay the same. So if you're flipping a coin, heads and tails, it's still 50-50, regardless if you just did 5 heads. You still have a 50-50% chance of landing on tails. The rule of large numbers. So statistically speaking, if you do that test infinitely many times, the probability of both of them should be getting to the theoretical experiment, which is 1/2 and 1/2. The experimental probabilities, though, are what actually happen. So the idea is the larger amount of options you do, the closer to the theoretical experiment probability that it gets. That's why I always laugh. So I love doing the roulette table when it comes to gambling. And I always laugh listening to everyone going, "Oh man, these numbers are hot," and they're like, "We're gonna put a bunch of money on this one." I'm thinking, it's still the same odds that hits that number and that number. So, um, they flip them every 15 minutes. So even if they have a pattern, you're not gonna be able to tell. Yeah, especially if there's like a lot of winners, they'll flip them sooner. If there's like not many people, they'll last a little bit longer. But yeah, they do that with card hands too, so that people can't identify patterns with the other folks. So that is stuff that people do that are trying to look for patterns. They're like, all right, he flips the risk at this speed, and the ball's now steadily going here, and so they'll start doing math and stuff. And then when they kind of see that happening, they'll switch the guy, bring another guy in, and then the whole speed is just completely wrong because this guy will be like, boom, and the ball like barely go in circles. The other one was like, anyways, yeah. So you're probably right. There is probably a variable that we should calculate with the spinner and the rotation of it, but to be able to find that variable in the time that you'll have that the person there isn't is yeah. Yeah. All right. So recall that the mean is the same thing as NP. Remember, N represents the sample size, P is the probability of success, and the standard deviation is just the square root of the sample size times the probability of success. Remember, Q represents the probability of failure. For the binomial distribution, a normal distribution can be used to approximate the binomial distribution when the mean is basically greater than 5. And then when NQ also has to be greater than or equal to 5. So remember, the sample size times the probability of success and sample size times the probability of failure both need to be greater than 5. Last time we did this, I think in chapter 7, I didn't make us do the test, but I think I did it anyways with y'all, and we got like 138. But always check to make sure that these two do give you greater than 5, or we will not be able to use this. All right. So the standard normal distribution can be used to test hypothesis for proportions. So the test statistics for z-test for proportions is as follows. I'm pretty sure this is the same as what we saw in chapter 7. You're going to take your probability of success of your actual sample minus the probability of success of what you're trying to get. So let's say we have a 50% probability we think there's a 50% chance probability of landing on heads. After doing 22 different samples, I got a probability of landing on heads as 0.42. So then now you have 0.42 and 0.5, and then you'll kind of plug that stuff in. Where again, you would have your probability of success and failure with the actual probability, not with your statistics. So this will be 0.5 times 0.5 in our case of heads or tails, and then divide it by whatever your sample size is. Any questions on how that formula works? Go ahead. P hat is your actual probability of your experiment. Oh, you're talking about for the blanks? Right. Yeah. So that's going to be the act, like the more of the theoretical, where this is the experimental. Yeah. So this will be 0.5 times 0.5 if I'm flipping a coin. Yeah, this p hat here, that's your experimental. So let's say we get I don't know, we flip the coin 22 times and we get a 42% chance that it landed on heads. This p of probability of success, let's say I want it to be on heads, is 0.42, but the probability of the theoretical is now going to be 0.5, and the probability of failure is also 0.5. All right. So, anyways, and we'll do some problems that'll kind of make more sense. All right. Where p hat can also be found by taking whatever it is that you're trying to get, let's say heads, and then you divide it by however many sample spaces are, or whatever the I don't know what. There you go. And then that right there would be your probability of whatever the sample is divided by the n. We'll do some problems with that to give more meaning to this right here. But this right here would basically be your sample proportion. So this is basically what happens. And then P is the population proportion. This is usually what should happen, or someone gives you odds, right? They'll say that someone shooting free throws gets 75%, but then we follow somebody else and we saw that they're 0.62 and we want to check some statistics on that, or whatever the case might be. All right. And then N is again just the sample size. All right. So let's do a couple examples of this and then we should be good for today. All right, so the formula derived that we got for the z-test, which is the sample mean minus the population mean divided by the standard deviation. We're just going to substitute the population mean with what we get for proportions, which is the n times p, which is the sample size times the probability of success, and then replace standard deviation with the square root of the sample space times probability of success times probability of failure. And therefore, you would get more of a formula that looks like this. Sorry, my head went somewhere else. All right, so that's kind of what we'll get. Same type of process. So assumptions for testing and proportion. We're going to assume the sample is random and not rigged. Two, the conditions for a binomial experiment are satisfied. Remember, that means that there can only be two results, the probability of success and the probability of failure. There's not a third option. And then also that the NP is greater than 5, and so is the QP. Go ahead. Yeah, it's my Q's. You don't like my Q's? I can see that. Yeah, Q though. I do my twos with like a loop, typically. All right, so let's get into the first example then. So this is talking about a female physicians, and it looks like, oh, they didn't do it all for you, but it says the percentage of physicians who are women is 27.9% in a survey of physicians employed by a large university health system. 45 of 120 randomly selected physicians were women. Is there sufficient evidence at a 0.05 level of significance to conclude that the portion of women physicians at the university health system exceeds 27.9%? So just like we've been doing, our null hypothesis will be the equal. So we're going to see, is it 27.9? And then the percentage there, where are we at? Exceeds would mean what? Greater than, more than, stuff like that. So our alternative hypothesis will be probability that it's greater than 27.9. The portion of the women physicians, the university system is larger than 27.9. This is the research claim. So what's our research claim? Is it the null or is it the alternative? The alternative. Again, we're trying to see that if it exceeds 27.9. Our alpha is, sorry, what was the question? Oh, so our alpha is 0.05. That indicates our significant level. So let's do a z-test. Go back. So there we go. So our z-test here. Where is my pen? All right, so the first one was the sample. So what was the sample? That would be the population. So what is 45 out of 120? I don't think 2. Because 60 would be 5. I'm thinking it's going to be in the 4s or 3s. 0.375. Oh. Oh, is there answers already on y'all's paper? Oh, that's okay. That's what we're going to subtract as our population mean. So our sample mean we got was 45 out of 120, which y'all told me was what? 375. Exactly. So that'll be our probability, our population mean, which was 0.279. So what are you talking about? It says the oh, I see. Yeah, that's what. So you're saying it didn't say population. So what we can conclude is since it then says a survey or a sample was done, and then we got a 45 out of 120, now we know that one at least is the sample. So the other one must be the population. But you're right, it does not specify, and that population, I think, is just over all physicians, I guess, and maybe the country, but then the sample is only done that's employed in a university health system. So we don't quite know if the population is going to be the entire health system or just the people at the university health system. But we can state that since 45 out of 120 is what my sample survey is, that I can conclude that this one must be my population, even though I don't quite know where the population is. That makes sense? So it doesn't say it, but we can kind of conclude with some context. Yeah, so this right here ends up actually being the NP. It did it for us, so we don't got to multiply or do anything with this. But yes, on the bottom, we would then need to do I think so. Because yeah, because that's already been done for us. Um, is the NP, right? Which is what we typically get. If we weren't told, maybe we would have to do it if we were told like the probability success. But you're right. I would almost want to take that 0.279 and multiply it by 120. But that's not. No, it's in it according to our formula, it said that the population mu is our NP. But it's stating here that that 0.279 is the NP. So it's already like been done for us. Correct. So that's why I was saying that this right here is typically known as the mu. which is our NP, but it was given to us. So we don't have to take that and multiply it by 120 for our sample. So that's this next part here. So on the bottom, now you have your N times P times Q. So this would be your 120. Oh, wait, actually, sorry, what's the formula? It is. Where'd you get the divided by N though? The next page. The page before? It would. I guess we're not using that equation yet. Okay. So yeah, so this mu here is then our P, our probability of the population, and this is your P hat, which would be the probability that you got, which was 42 out of 120. And then you're right. Then it's going to be probability of success, which is 0.279, times the probability of failure, which would be yeah, 721. And then divide that by my N, which was 120, all in the same square root. So now we got to figure out what that is. And it says round to 2 decimal places. So let's see what I can do with the fancy dancy calculator here. 0.375 minus 0.279 divided by parentheses 0.279 times 0.721 divided by 120. But I want the square root of that. Yeah, this calculator wouldn't let me do it. I'd almost have to see that's 0.096. I'd have to write that number down, and then I'd have to go 0.279 times 0.721. 0.279. Do you remember that first number? What is 0.375 minus 0.279? I know, but I put it on my paper, but I didn't actually write it. What's 0.375 divided or 0.375 minus 0.279? 0.096. Remember that number, 0.0409. I got that? Okay, what was the number you just said, Ella? 0.096 divided by 2.34? Perfect. All right. I had to do that by hand, I guess in steps. Like it wouldn't let me do the whole thing in a square root. Yeah. But 2.34, that is the answer. I was just trying to do it in a non-fancy calculator. I put it in portions. All right, but we got what 2.34 rounded to 2 decimal places. So now we need to go to our z-score table and figure out. Actually, you should have this memorized, but you need to figure out what your critical value of z is at a 0.005. Remember what kind of tail test is this? Right, so it's a one-tailed on the right, so I can go straight to I guess I would have to go to 0.95 since it's on the right side. And at 0.95, what is the z-score? 0.16 or 1.65. Hopefully you have that memorized. If not, again, just use the z-score table. So that is our critical value there. So for the right tail test, oh, I didn't even know I said that. The test statistics to the right of the critical value indicating to what with the null? We're going to reject it. it is definitely not equal to 2.79 or 27.9. So we reject the null hypothesis. The p-value is, how do we calculate the p-value? The two, let's say that again. I gotta go back. How did we do the piece value last time? I'm going back to chapter 8. We did p-value earlier. Oh, that's right. The p-value. Probability. We need to find the probability value, which is going to be under 2.34. Yeah, sorry. Hello? Hmm. We're in the middle of a lecture. Could we do a different period, or maybe I can send her afterwards? All right. Yes, ma'am. No, bye. All right. Yeah, so sorry. That's where we go to the z-score table, go to 2.34. What is our value? 9904. But this is a right side. So that means I have to do what with this value? And you get what? Yep, that's right. Okay. So we get 0.0096. Um, so we'll write it again, I guess. It's less than our region here of 0.05. So therefore, there what? First word is starts with an I. There there is sufficient. I don't think that's how you spell it though. Good. There is sufficient evidence to support the claim that the proportion of women physicians at the university health system exceeds 27.9%. So we reject the null. So therefore, it must be not equal to that. So we can definitely say that we have evidence that supports our claim, but we're not going to say we're right. That's why we have type 1 and type 2 errors. Because the only way to get the actual answers is to do the entire population. And typically, again, when you're working for a company, they're trying to get an estimate to see if it's worth putting out on the shelves or something like that. And then afterwards, they'll go back in a year and go, all right, this is what actually happened. Was it a type 1, type 2, or were we correct? The only thing you wouldn't go fix is if you like reject the null, you'll never know if it was right. Or sorry, failed to reject, and you're like, okay, that's not going to be that, so we won't do it. Yeah, and then you won't test it because obviously you're like, well, there was enough evidence, I guess, to say that we would lose money. So then you'll never know really if it's a type 2 error or not. Yes, you're just saying with confidence, I'm 95% confident that I'm right. There you go. All right, so this is the last question, and then I'm done for today. This says exercise to reduce stress. Seems like you have a lot of stress in your life, but we're gonna exercise this out, right? So a survey. Oh my goodness, survey. A survey by Men's Health magazine stated that 14% of men said they use exercise to reduce stress, wherein use a sufficient critical value of 0.02. A random sample of 100 men was selected, and 12 said they exercised to relieve stress. I feel like that number's a little high. 12, I don't know, out of 100, it should be like 1. All right, use the p-value. It depends on where they're testing too, because they're like at the fitness center or something like that. All right, was that convenient sample? Boy, I guess we'll have to assume this is random. Anyway, so going to use the p-value method to test the claim. Is it reasonable to generalize the results to all adult Americans? Do these 100 men basically tell us everything about men in the country? Or in, yeah, 14% of men said they used exercise. And then a random 700 men. Where you seeing adults? Oh, yeah. Reasonable to generalize the results to all adult Americans. It really should say all male adults. Oh, maybe. So again, the Neal hypothesis is always going to be what it's equal. So we're saying that's going to be the 14%. That is what we're saying is the claim. Is it reasonable to generalize these results? So we're not seeing if it exceeds or is less than. But then what would this be then? Good. P is not equal to 14% or 0.14. I guess if we had to write this in words, how would you write the researcher's claim for the null hypothesis here? Don't use P. Like what's these like words? Perfect. They put that in the complete opposite direction, but that was the exact same wording. So this one just says the percentage of men who say they exercise. I think I added an extra C. You don't see this. Exercise to reduce stress is 14%. But I would have totally took your answer when you just said 14%. And then it's almost like doing Yoda's thing here on this one. Blah, blah, blah is 14. All right. Anyways, um, how would you write this one in words? Exactly. It's going to be the exact same sentence with the word not right there. And then what was the alpha that was given? That's what we're going to do next. All right, so the test statistics here, if we work this out, again, do your population probability of success, which we see is 12 out of 20, which is just 12 out of 20. Thank you, which if you don't know is 0.12 minus the actual result, which was 0.14, or the population result, I guess. And this was the sample result. Divided by the square root of probability of success, which is 0.14, times probability of failure, 0.86, divided by 100. I'm just going to take your word this time for it. It's going to be a negative. What's up? Is it hard? Uh, dang. Go back to it. We haven't used it yet. Maybe not. I don't know. I will say sometimes when y'all ask me questions, I'll go on to Alex and look at the explanation and go, "Oh yeah, that's right." Sometimes I can just I see it and I just know the answer, but statistics is not as I'm way better at college algebra I've seen. I can do the algebra quicker. Was it? Perfect. If we round to two decimal places. And the critical value of Z is what? So 0.02. Ella, you are dead on. We do need to cut this in half, but why are we cutting this in half? Because it's a two-tailed test. So I need to find out at 0.01. This will be a plus or minus. So again, use your Z score unless you have this memorized. What is 0.01? I don't have this one memorized because this is a 98% confidence level. We haven't used 98% confidence. Hmm? That's what this got too. What is it? There it is. Plus or minus 2.33. Yeah, I wouldn't expect y'all to have that one memorized because that is we don't have a 90 we didn't practice 98% confidence. That's what 0.02 significant levels would be. Go ahead. Oh, is it? Perfect. It wasn't on our chart, but good. I mean, you'll eventually do this so many times, like 10 times in a row, that you'll eventually just have these memorized. Well, I got 10 more for you. All right, last part here. We did that part, right? Okay, so here we go. So the area on the Z table associated with negative 0.58 is what? No, bring it back, bring it back. Remember, this is going to be on the left side or the negatives. 0.2810 is correct, okay? This is a two-tailed test, so double the area. So we'll take this probability right here and multiply it by 2, which was 0.2810, and we get, and that is greater than 0.02. So there is what? If it's greater than our significant level, there is not enough support. So there is not sufficient. No, doubling is times 2. Yeah, I took the 0.2810 times 2. I might have said that in my head. That's probably I might have been adding in my head just so I could try to all right, do it. So not sufficient evidence to reject the claim. Yeah, so there is not sufficient evidence to reject, so we fail to reject the null hypothesis. Do what? We think it's true. But we're not going to say it is, but with 98% confidence, we're saying it's true. To reject the null. What? Because remember, the null hypothesis was our claim. Go ahead. Right. Yeah. So we don't have enough evidence. Now we have enough support to suffice to support to rejecting the claim. So in this part here is it is or is not reasonable to generalize the results. It is not reasonable to generalize the results to all adult Americans because the population for which the sample is selected is, it just says not all adult Americans. And that's all I got.